Okay, students, welcome back to finding the upper lower bounds, supremum and infimum of sets. In this case, we're going to be doing another example, part two. Uh, you can click down here to take a look at part one video if you want. We're going to take a look at two examples in this clip. Okay, so for example two is a continuation of the other clip. We're going to be doing basically the same procedure that we did in example one. Okay, so the instructions are as follows. Find the upper bound, upper bound, supremum, lower bound, and infimum for the given set, for the given set S, which is the subset of real numbers. In this problem, subset of reals. And then after finding all these information, state, or you can do it while doing the problem, state if the supremum, I can just write sub of S, and the infimum, inf for short, of S are included in S. Okay. All right. So in this problem, we're going to be doing the example S, which is a set X such that the absolute value of 2x plus 1 is less than or equal to 5. All right, so this is what we're going to do. All right, so let's start by finding out what the upper bound is. But first of all, even before I want to start, I want to look for the set of x's that satisfy this equality. So what set of x's satisfy this equality? To do that, I'll just simply solve this absolute value inequality. Absolute value of 2x is less than or equal to 5. Then I know that absolute value can be written as plus or minus 2x plus 1, less than or equal to 5. And I can write this as a sandwich inequality. Negative 5 is less than or equal to 2x plus 1, less than or equal to 5. And subtract 1 from all three sides of this equation. So I'll have negative 6 as less than or equal to 2x is less than or equal to 4. And then divide everything by 2. My final answer is going to be negative 3 as less than or equal to x, which is less than or equal to 2. All right. So let's sketch what this inequality looks like, and basically see what our solution set will be. Okay. So on the number line, we're going from, say this is 0, 1, 2, 3. We're going from negative 3 to 2, 1, 2. So we have a closed set. This is closed. So this bounded interval are the set of real numbers that satisfy the original equation. Absolute value of 2x plus 1 is less than or equal to 5. All right. So with this set of real numbers right here, between, from negative 3 and 2, everything included in the center, what values of x, what is the supremum of, what is the upper bound? Let's do upper bound first. What's the upper bound in this interval? All right. So let's do the upper bound first. Upper bound. All right, so before we find out what the upper bound is, let's just go over what the definition of upper bound is again real quick. So a set, just some real quick definitions. A set S has an upper bound, or is bounded above, has an upper bound if there exists, let's call it B, a B, there exists a B in R such that for all x's in S, x is less than or equal to B. Okay, so you know that in this problem, S is a subset of all real numbers, right? So we can see that S has an upper bound, namely B, if there is this B in R such that for any value you pick in S, that value is guaranteed to be equal to or less than B, okay? And then the smallest possible value, the least possible upper bound, the least upper bound is the supremum. Okay, so the least upper bound is the supremum. Okay, you have to realize here that the upper bound is not unique. Okay, any number that satisfies this, the number that satisfies this, and everything bigger than this number, all those numbers are all upper bounds of S, because any element you pick on S, since B is bigger than them, any number bigger than B is guaranteed to be bigger than any number that's in S. So upper bound is a collection of elements that satisfies a certain requirement, but the least of all those basically gives you your supremum. Okay, so let me just make an interval notation just to illustrate that real quick. So let's say we have a closed set right here, B. This is the upper bound, because when you go into the right on the number line, it gets bigger. So since this is the upper bound, let's make this as a set. All the elements in here are set. All the elements in here, all the numbers, the real number line, create S, okay, which is a subset of the reals. So this is an upper bound, okay, because everything in S, any number you pick right here, they're all less than B, okay? But guess what? Any number bigger than B, let's say you pick a number here, B1, another one, B2, any number greater than B are also upper bounds, okay? But if you order these, the least of all these upper bounds will give you the supremum. This is the supremum of this set right here, okay? All right, so with that in mind, what's the upper bound here? In this case, we know that this is bounded above by 2. That means 2 and any number bigger than it will be the upper bound. Okay, so I can write it as x such that x is greater than or equal to 2. Okay, so any number 2 or greater bounds this set from above. All right, so we have this collection of numbers as the upper bound. What is the supremum? The supremum of S, or the least upper bound. Okay, supremum of S, or loop. We call it loop, loop of S. The supremum of the loop of S is the smallest of all the upper bounds, which is 2. So the supremum is x equals 2. That's the supremum. Okay. All right. Now, is the supremum, is it included? Is it in S? Is this part of S? Absolutely, since we have a closed circle here. So the answer is yes. All right. Okay. Now let's find the lower bound. What is the lower bound? Okay. Before we find out what the lower bound is, let's write down the definition again. Review the definition. So a set S has a lower bound. If there exists, let's call it A. Okay, there exists an A in R. Okay, because S is a subset of R. If there exists an A in R such that for all the x's that you have in S, you guarantee that they're all going to be bigger than or equal to A. Okay, so this is your lower bound right here. Okay, and the greatest of all these lower bounds, the greatest lower bound, GLB, the greatest lower bound is the infimum. Okay, is the infimum of S. All right, so if you look at this set notation I have right here, this is the lower bound. This is one of the lower bounds. Any number to the left or any number less than this is guaranteed to be a lower bound also, because they are less than any element contained in S. This is the greatest of all the lower bounds, so this makes A the infimum. Okay, so this is the infimum right here, and this right here is a supremum. All right. Okay, so let's include that. Yeah, I already said it. The greatest lower bound is the infimum of S. All right, so if you look at this inequality right here, the lower bound is -3, and anything to the left of -3, right? So x, such that x is less than or equal to -3. All these are the lower bounds, okay? So the infimum is the greatest of the lower bound. The inf of S, or the greatest lower bound of S, is x equals -3. All right. So next question is the infimum of S? Is it contained in S? Is it? Absolutely, since you have a closed circle here, so the answer is yes. All right. Okay, when you're doing problems, supremum or infimum examples involving real numbers, it's very easy to work them out. Let's take a look at a case now where we're dealing with a smaller subset of numbers, which is the rationals, okay? So let's take a look at the rationals right here. So example 3, we're going to do the same process, but we're looking at a smaller subset, okay? So find, in this case, I don't need to write an instructions again. In this case, let S be a subset of the rationals, okay? Let S be a subset of rationals and S be defined by x such that x squared is less than, let's say, 5. Okay? Alright, let's do this. So we're going to be real careful here because we're dealing with rational numbers, okay? And we know that rationals have gaps in them, so we're going to be really careful here. Alright, so first thing we want to do is we want to first of all find a set of numbers that satisfies this inequality. And then we are going to find the supremum, if it exists. I'm sorry, the lower bound, supremum, and all that cool stuff. All right, so let's find what the set of x's that satisfy this inequality. So we have x squared that is less than 5. And then what we're going to do next is let's isolate the x. So we take the square root of both sides with this, with that. And then we have absolute value of x is less than root 5. Alright, so that becomes like the other problem we just did. Plus or minus x is less than root 5. So we have negative root 5 is less than x, or x is less than root 5. Okay, so these are the set of x's that satisfy this inequality right here. Alright, so let's look for the upper bound. The upper bound. Okay. So for the upper bound, what is the biggest wait a minute, let me draw a sketchy number line for this so that we can have a good visual of what we're dealing with here. So we have negative root 5 and root 5, close circle here, close circle there, and a line going, oh wait, I'm sorry, they're both open circles, because we do not have a line of inclusion under this inequality. So open circle, connected. Alright, now, let's see, upper bound. So to find the upper bound, the question is, we need to find the smallest rational that bounds, no, we want to find, yeah, let's find what is the smallest rational that bounds this set from above, okay? We know that root 5 is an irrational number. It's not in the set of Q, right? So that means we need to pick the a rational number that is smaller than root 5. Okay, so the question is, what is the greatest rational number, that is less than root 5? Okay, that is less than root 5. Okay, we know that if our set were real numbers, that's easy. This will be the upper bound, and anything bigger than it will also qualify as an upper bound. But if we look here, this number root 5 is not in the set of rational, so it cannot be included. So the question is, what is the biggest rational that is bigger than root 5? And the answer is there isn't any. Any rational number that's arbitrarily bigger than that is less than 5 that you think is the biggest, you can always find another rational number that's bigger than it. Okay? So for example, let's say we were going closer to, let me just pick an arbitrary number. You're going close to 1, for example. Oh no, let's say you're going close to 1. Okay? And then you have, let's say you're going to 0. I think that would be a better example. It's much more visual. If you're going close to 0, going close to 0, and what is this biggest rational? What's the smallest rational that's close to this? You say, oh yeah, how about 1 over 10? All right? or you can find another one 1/100. So there are infinitely many rationals that are close to here. Okay, just as the case of root 5. If you pick any number, you want to find the smallest rational before it, you're going to have problems because there are infinitely many rationals that are less than this. So the upper bound in this case, there are no upper bounds. There isn't any rational number that is smaller than this that's bigger than everything else because it is non-existent. All right. So what does that mean about the supremum then? The supremum is the smallest of all the candidates. But guess what? We don't have any candidates, so how can we pick the smallest? So the supremum, there are no supremums. Okay. How about the lower bound though? The lower bound. Now we're going close to root 5. Okay, going close to root 5. Now the question now is similar to this. What is the the smallest rational, the smallest rational, what's the smallest rational that is greater than, that is greater than root 5? I mean negative root 5. What's the smallest rational here that's to the right of this? The answer is there isn't any, okay? Whatever rational you pick you think is the closest, you can always find another rational that is smaller than it, okay? There are infinitely many rationals that are really close to negative root 5, all right? So guess what? There are no lower bounds here. There isn't any q that we can say is the smallest, is the biggest number that's smaller than everything in this subset. There are none. So guess what? The infimum does not exist. There are none. Okay. Had it been that we had a rational number here, that number would be the lower, that would be one of the lower bounds and every rational bigger than it, and that would be the supremum. Okay, so when you have rationals bounded by irrationals, then you can have a supremum or infimum in the set of rationals. Okay, so there goes your answer for this situation. Alright, so thanks so much for watching this video. Please feel free to subscribe to my videos for more updates. And you can request videos. Collection of more clips can be found on untitled.com. Thanks again and have a wonderful day.